Hello, and welcome to our discussion of section 4.5 from our calculus textbook. The topic in this section is called L'Hopital's rule, and it's an alternative means from what we've studied already for finding limits of 0 over 0 or infinity and infinity over infinity indeterminate forms. So just a reminder about this. The reason why we call these indeterminate is because we're getting conflicting information from the information that we're getting from the numerator and the denominator. For instance, in a 0 over 0 form, if the limit of the numerator is going to 0, we expect, in this case, if the numerator of a fraction is getting small, we're expecting that the limit is going towards 0 as well. But if the limit of the denominator is going to 0, well, dividing by a tinier and tinier number makes us think that the value of the fraction should be getting very, very large. And so we've got this conflicting information between the information imparted from the numerator to the denominator. And so in the past we've seen we need to do some algebra like factoring or multiplying by a conjugate or dividing by the highest power of x that appears in the denominator, some algebra that will allow us to see what's going on with these limits through some sort of algebraic means. In this section, though, we're going to be looking at a method that involves derivatives. And so we've got L'Hopital's rule, and the assumption is that we've got a 0 over 0 or infinity over infinity form. And L'Hopital's rule says that the limit of the ratio of f and g is equal to the limit of the ratio of their rates of change. If we can't get an answer by comparing the ratio of the values of the functions, we're going to look at the ratio of how fast they're changing. We're not going to try to prove that here in this course, but it turns out that it's a very useful tool. I will point out in this last sentence that it's quite possible that this expression will also turn out to be indeterminate, and in which case we would wind up applying L'Hopital's rule to it, and therefore looking at the ratio of second derivatives and seeing what's happening with the limit of that. So be aware that we might apply L'Hopital's rule multiple times within a single problem. But we also always are going to want to check that we've got one of these indeterminate forms. So let's look at a few examples. Our first one is the limit as x goes to 9 of x minus x to the 1/2 minus 6 over x to the 3/2 minus 27. We should verify that this is indeterminate. So let's look at the numerator. I can just use direct substitution on this. 9 to the 1/2, that's the same as the square root of 9, or 3. And so that limit is 0. The limit as x goes to 9 of x to the 3/2 minus 27 is 9 to the 3/2 minus 27. 9 to the 3/2, we take the square root of 9 to get 3. We cube that, we get 27. So this is indeed 0 over 0. And so the way I'm going to indicate that we're using L'Hopital's rule is with an equal sign with an L period H period over it. And so we're going to calculate the derivative of the numerator, calculate the derivative of the denominator, and then try to see if we can use substitution on that. So notice that we are not applying the quotient rule here. We're taking the derivatives of numerator and denominator individually. We're comparing the rates of change of the numerator and the denominator. So by L'Hopital's rule, I get 1 minus 1/2 x to the minus 1/2 as the derivative of the numerator, and the denominator I get 3/2 x to the 1/2. And let's try substitution. Well, I'm going to get 1 minus 1 over 2 times 9 to the 1/2 at the top, and I'm going to get 3/2 times 9 to the 1/2 on the bottom. 9 to the 1/2 is 3, so I get 1 minus 1/6 on top. I get 3/2 times 3 on the bottom. That's 5/6 divided by 9/2, which I can rewrite as 5/6 times 2/9. And it looks like I can do a little bit of canceling here, and I would get 5/27. So that was not an answer that I might have expected going into it, but that turns out to be the result from L'Hopital's rule. Our next example is an infinity over infinity form. If I look at the limit as x goes to infinity of 6x squared minus 4x plus 1, I look at the leading term. As x gets really big, 6x squared is getting really big, and so we would say that this limit is plus infinity. My limit in the denominator is limit as x goes to infinity of minus 3x squared plus 7. Again, we look at the leading term. X is getting big, x squared is getting big and positive, but we take negative 3 times that, we get minus infinity. So the signs don't matter. I've got infinity over infinity. And so it doesn't matter whether it's plus infinity over minus infinity over minus infinity, just that both of them are getting very large in magnitude. That's the important thing here. So I can apply L'Hopital's rule. And so that's going to be the limit as x goes to infinity of 12x plus 4 over minus 6x. And this is still infinity over infinity. As x gets big, 12x is going toward positive infinity. And as x gets big, minus 6x is going toward minus infinity. So I get to apply L'Hopital's rule again to this. And so it's going to be the limit as x goes to infinity of 12 over negative 6, or the limit as x goes to infinity of negative 2, but the limit of a constant is just that constant. And so my answer is that this limit is negative 2. Notice that that is what we expected. Based on things we've seen earlier in the course, we talked about if the degrees of the numerator and denominator are the same, we expect the limit to be the ratio of the leading coefficients, and that is 6 over negative 3 or negative 2. Here's another example. Limit as x goes to 0 of e to the x minus 1/2 x squared minus x minus 1 over x cubed. Let's take a limit of the numerator. Well, that's going to be e to the 0 minus 0 minus 0 minus 1. E to the 0 is 1. So 1 minus 1 is 0. So far, so good. Limit as x goes to 0 of x cubed is also 0. So this is 0 over 0. So I get to apply L'Hopital's rule. The derivative of e to the x is e to the x. The derivative of minus 1/2 x squared is minus x. The derivative of minus x is minus 1. And then I get 3x squared on the bottom. Limit as x goes to 0 of e to the x minus 1. Still 0. And the limit as x goes to 0 of 3x squared, also 0. So this is still 0 over 0. So I get to apply L'Hopital's rule a second time. The derivative of the numerator is e to the x minus 1. The degree of the denominator is 6x. Limit as x goes to 0 of e to the x minus 1 is e to the 0 minus 1. That's still 1 minus 1 or 0. The limit as x goes to 0 of 6x is 0. So L'Hopital's rule, yet again, the derivative of the numerator this time is e to the x. The derivative of the denominator is 6. This is 0, not infinity. And so now I can try substitution, and I get 1/6 for my limit.